Hello, everyone, and welcome back to your channel of probability. Um, Last session, we were done with the discrete random variables, and we looked at some models or some mathematical models, meaning distributions. Today, we will start the continuous random variables, which are pretty much more important in statistics. Continuous random variables. So what is the difference between discrete and continuous, as we said? In discrete case, we said that X, your random variable, can take on specific values. So most likely counts, not necessarily, but most likely counts. So you can have probability that X equals 0 or 1 or 2 or 3, but not 1.5, not 2.25, and so on and so forth. In continuous, no, X takes on any value within a range, which is the domain of the function, okay? The values of X. And this domain may be finite or infinite. It doesn't matter. We refer to that probability that defines, the X's as the PDF or the probability density function. Remember, we called it that the probability mass function because the X's can take specific points. So remember when I told you we will assume these are weights and we try to find the fulcrum that would keep this bar connecting the weights horizontal. That's why we call it mass, but here we say probability density function. And we refer to it with lowercase f of x. The cumulative distribution function, and we usually write it in capital letters, this is written as uppercase letter of f because this is the integral of that. Cumulative, or just the distribution function, cumulative distribution function. Okay. Now, some stuff you have to be careful about. In the continuous random variable, if I say, what is the probability that my random variable x equals a specific value x, that probability is 0. Say what? Why couldn't the x equals 2, for example, if it's within the domain? Well, remember, excuse me, in the case of a discrete random variable, and suppose let's take a very easy, simple example of rolling a die again. Yes, again. We have 6 equally likely events. So the probability that any one of them occurs is 1 out of 6. You divide the event over the total number of events. Nice. Now, assuming I have my function is between, say, even 0 and 1. Only 0 and 1. And it's equally likely. How many points exist between 0 and 1? Yes. 8. Oh, I'm sorry, just hit it down. Infinity. Yes, infinity. So, what is the probability that x takes a specific value out of these infinite values? Much, much worse than the lottery, right? It's 1 over infinity, which is 0. So really, if we tell you find the probability that x is less than 2 or less than or equal to 2, it doesn't make any difference in the continuous word. Maybe it makes a huge difference in the discrete realm, right, of things. Like you have to specify whether either is it less than or equal or just less than, greater than or equal or greater than. Here, I don't care. If I say the probability that x is between 1 and 2, I can say greater than 1 less than 2, or greater than or equal to 1 less than 2, or greater than 1 less than or equal to 2, or greater than or equal to 1 less than or equal to 2. All these 4 things are the same. Notice that a probability, the function that we draw can be anything. Let's say something that looks like that. And here is A, here is B. It can be, by the way, the domain may be finite like this case, or it may be infinite, going from negative infinity to positive infinity. here, the height at any point is just the function f of x, right? So if I tell you what is the probability that x equals this value, you'd say, well, it's the area under the curve at x, but x is a line, and the line is the area of the line is 0. And that's why we cannot take a value exactly at x equals 2. But I can tell you, find the area or the probability that x is between 1.999 and 2.001. Yes, you can, but not exactly at 2. Because in order to find the area has to be a rectangle. And we say, well, if we take this as delta x and then make it smaller and smaller until you get to the limit as delta x approaches 0, remember what we call that? Yes, dx. So this is the probability, not the line. F of x cannot be negative. So it's greater than or equal to 0. I will never have something below the x-axis. It's impossible. And then the integral from negative infinity to positive infinity, or from a to b, because that's the domain in this particular case of f of x dx equals 1.0. Like we did also in the discrete case, we will define mu of x, or the expected value of x. And then you will see something that would help us later. Equals the integral from negative infinity to positive infinity. There we said x times p of x. Here I'm going to say x times the probability of x, which is f of x dx. So if I take the integral of f of x dx, I get 1, but I multiply by x first. And the area under the curve is 1, so really this is the centroid of this shape. Exactly. And if I want to find the variance of x, remember how we did it? We said it's the integral from negative infinity to positive infinity of x minus mu x quantity squared times f of x dx. And we said this is, since I already know mu, there is no reason to subtract it. It's hard. Remember what we did there? In the discrete case, we said it's the integral from negative infinity, or the equivalent to that would be x squared f of x dx minus mu x squared. That usually is easier to perform or to apply, but both are correct. Okay, so now we learn how, for a generic thing. So let's take an example of a case where I have f of x, maybe it's the load of cars going over a small bridge. And that value is 0 if x is less than 0. Of course, it cannot be less than 0. And x is in tons, a moving load. X can be greater than 0, less than 2. And as we said, I don't care if I say greater than or less than, or greater than or equal, less than or equal. It's some function. And x greater than 2 is 0, or otherwise it's 0. We want something that when we integrate, we get 1. I think I made up some numbers and I got 3x over 8, I think. I did that. We can check. I'm sorry, let me do that. I'm going to take the integral of that from 0 to 2 and see if I get 1. If not, then we will correct it. Okay, so I get x over 8 plus 3x squared over 16 evaluated between 0 and 2. So this would be 2 over 8, or a quarter, plus 3 times 4 over 16. Yeah, 3/4 plus 1/4 equals 1, so it's correct. Okay, so now I want to ask you, find the probability that when we check at some point in time, the load x is greater than 1, less than 1.5. What is the probability that x equals that? Okay, very simple. I will take the integral between 1 and 1.5 of this function. We already have it, right? So we already have it, but instead of 2 and 0, it saved us time. So of 1/8 plus 3x over 8 dx equals x over 8 plus 3x squared over 16, evaluated from 1 to 1.5. Again, to save time, we can do that with a calculator, right? So I'm going to go to math and go down to the finite integral. The integral is from 1 to 1.5 of 1 over 8 plus 3x over 8 dx. And it's roughly 0.297. Roughly 30% of the time. Of course, you can draw this function. Really, it's very easy, right? Because that's a linear function. Y, in fact, the y-intercept is 1/8. So basically at x equals 0, you have 1/8. And then at x equals 2, you have 7/8, right? 3 times 2 is 6, plus 1 is 7 over 8. So something like that. This is 7 over 8. 1 over 8, not 1.8. And it's as if I'm asking you, where is the centroid? No, I'm sorry, we are not finding. What is the area between x equals 1 and x equals 1.5? So this area. In fact, you didn't need integration, right? You just substitute x equals 1. So when x equals 1, this would be 3 plus 1, or this is 0.5, right? 4 over 8. And when it's 1.5, you get, this is 4.5, 5.5, meaning 11 over 16 at this point. We know the area of a trapezoid is the average of the two parallel lines times the height, which is 0.5. So let's do that and see if we get the same result. You get 0.5 plus 11 over 16, close the parentheses, over 4 times 1/2 over 2, meaning divided by 4. Yes, sir. Exactly the same thing, right? We didn't need. Second thing, I'm going to ask you, what is E of x? Meaning, what is the mean of x? Of course, if I'm between 0 and 2, notice not to scale. 1 is in the middle, but this is heavier. So I know that the mean has to be greater than 1. How greater than 1? Well, you can do it using the same method of centroids that we learned in statics. You will have a rectangle as well as a triangle, and you just need the x bar. I don't care about the y bar, right? We are looking at the mean of x, not mean of f of x. So but if we do it mathematically, it's the integral from 0 to 2. It's from -infinity to +infinity, but the function is only defined between 0 and 2. So you take the integral from 0 to 2 of x times that. So x over 8 plus 3x squared over 8 dx. That will give you the mean right there. We're not going to do the variance because it's, it's the repeat of stuff. So I will get x squared over 16 plus 3x cubed over 24. So it's 8 evaluated from 0 to 2, right? Because the 3 and the x cubed over 3 cancel, and you get x cubed over 8. Notice I don't care about the 0 because I get 0, so I just will get 2 squared over 16 plus 3 squared, 2 cubed over 8. So it's 1.25. Yeah, more than 1. Definitely has to be more than 1. In fact, we can find the median. The median is where is the line that the left area is zero point 0.5 and the right area is zero point 0.5. So the cumulative equals zero point 0.5. I take the integral of that and equate it to zero point 0.5. Because when I take the integral of that, if I take it from 0 to 2, I get the whole area. But if I take it from 0 to some point that I don't know, and I solve for it and equate that to zero point 0.5, I can solve it, but it's really not that important. But I just want you to start thinking in terms of, in the continuous case, in terms of integration. I'm going to introduce one very easy and important distribution is called the uniform distribution. That's the easiest one. And then I'm going to take a special case of that. The distribution is between 2 points A and B. Okay. But as the name implies, that distribution is uniform, meaning if you take any range, any equal ranges, the probability between them. So let's say this is 3 and this is 7. The probability that x takes a value between 3 and 4, or 4 and 5, or 4.5 and 5.5 is the same. Who can tell me if this is 3 and that's 7, what's this height of the PDF? This is x, and that's the PDF. What is this height? No, it's not 1. Some said 1. The total area is 1. That's a rectangle. If the base is 4, then the height should be 1 over 4. So when I multiply 4 by 1 over 4, I get 1. Okay? So really, if we want to describe it mathematically, we would say f of x equals, this is a and b, 1 over b minus a if x is greater than a, less than b, and it's 0 otherwise. Meaning the PDF, the CDF would be a triangular shape, right? Very easy. Yes, that's the cumulative. Now, so that's the function, right? What is the mean? This is 3 and that's 7. Yes, the mean a of x equals a plus b over 2. It's just the mean. It has to be exactly in the middle because it's symmetric. If you want a fulcrum or you want to hang this plate from the ceiling, you have to hang it at 0.5, at the point that is 5, not 0.5. At 5, right? Exactly in the middle, which is 3 plus 7 over 2, or a plus b over 2. And here I'm going to tell you that the variance of x, I'm not going to write it. I'm going to tell you something. And this story happened to me when I was starting my graduate studies, but I had my undergraduate in civil engineering and I switched to industrial. So they said, no, before you start, you have to take some introductory courses. In fact, I took some courses and I was taking a course in stochastic operations research, and it relies on it and on probability. So our professor was sick that day, and another professor came to gave the lecture. He started talking about, distribution quickly, the stuff we are doing now. And then he said, the mean. Who knows what's equivalent to a mean, or what? So many students raised their hands. We knew, of course, he talked about the center of mass or the centroid. So we said centroid. He said, yeah, nice. And what about the variance? So I raised my hand. He looked at me and he said, I was just making a joke. I said, but there is a variance equivalent to a variance. And he said, and what is that? I told him, I think it is the moment of inertia. And everybody laughed. They said, this guy is crazy. He's like, I felt so embarrassed when I said that. And then after the lecture, I went to his office and I said, "Sir, I wasn't making a joke on you or anything. It is really the moment of inertia." And I proved it to him through the uniform distribution. Do you know what is the moment of inertia of a rectangle? If you already had a course in, say, strength of material, or some people call it uh, anyway, um, in strength, yeah. Uh, you know that it's the height, if basically it's the base times the height cube over 12. Okay? That's the moment of inertia. However, because this area basically is one, so we said the base times the height cubed over 12, but the base times the height is one. So it's 1 times h square over 12. And what's the height? It's b minus a. Yes, it is b minus a square over 12. And the standard deviation, sigma, which is the square root of that, so it's b minus a over 2 root 3, is the radius of gyration. When you divide the moment of inertia by the mass and you take this, or here, if it's an area, you divide by the area and you take the square root, the area is 1, so you get that. Anyway, this is not a big deal, but I remember that we had this discussion before. Uh, just the last point, this professor ended up being my academic advisor for my PhD. And it wasn't, of course, on that, but it was funny that we became friends after that. We still are in contact, by the way. Okay, so the uniform distribution is easy. You see the mean, the variance. There is nothing else to say, except one thing. We have a special uniform distribution. We usually call it the standard uniform. And the standard uniform is the distribution that pretty much all computers are using it to generate random numbers between 0 and 1. And then if you don't want it between 0 and 1, you want it between, say, 3 and 7, they will get it from 0 and 1, add 3 to the number they get, and multiply the decimal place. So they multiply the decimal place by 4, and you add 3. So for example, if you get 0.5, I would multiply it by 4, because that 4, that's 1. You get 2, and then you add 3, so you get 5, which is exactly the mean. I use the mean. If you pick 0.1, then you multiply it by 4, and you add 3, you get 3.4. And you can see that 3.4 is 1/10 of that distance, like this is 1/10. So this distribution, of course, has a mean of 1/2 and a variance of 1 over 12, is the basis of generating random numbers. And then you can generate the random number, and we switch it into a random number, say, in any other distribution, like the distributions we are going to cover later. We will basically do the exponential and the normal. We'll spend more time on the normal because we will be using it more extensively in the second half of the course. Okay? I hope this was easy enough for you and that you enjoyed it. If you have any questions, as I said, you always drop me a line in the comment center and I will get back to you as soon as possible. Thank you very much and have a great day.